Last topic of this second unit. We're going to talk about just some applications of these trig functions. We're going to be using probably some inverse trig functions maybe along the way, but mostly we'll be thinking about just our straight old trig functions and how we can apply them. The first most basic application that we're going to use in our other applications is to solve a right triangle. What this means is that we're going to be just finding all the possible values, all the angles, all the side lengths, things like that. Then we're going to take that idea of finding all those angles and side lengths, and we're just going to push those into some application problems that maybe have a right triangle along the way. And if they've got a right triangle along the way and they want to know some value there, we can solve the right triangle. So it might not be completely obvious in a lot of these applications on how that right triangle plays into it. So that's some of the part that we'll talk about. But this shouldn't be terribly long. So we'll start with this solving the right triangle business. So like I said, solving a triangle is basically going to be to find the missing side lengths. Oops. Let me get my highlighter. That's what I meant to click. We'll be finding missing side lengths and angles. That's pretty much it. Our angles are going to be labeled with uppercase letters, A, B, and C. C is the right angle most of the time. And then the side lengths are going to be labeled with lowercase letters, A, B, and C, where C is the hypotenuse. Also, you might notice that angle A is opposite the side length, lowercase a. Angle B is opposite the side length, lowercase b, and angle C is opposite the side length, lowercase c. The right angle is opposite the hypotenuse. So that's our normal layout. That's kind of how we'll write these triangles. That's just standard notation so that everything is pretty clear when you're into it. Things that we should know. Complementary angles. We know that angle A and B have to add up to 90 degrees because the whole triangle has to add up to 180, and we already know this thing's already 90 degrees. Or if we're using radians, pi over 2. We also know the Pythagorean theorem. That's going to connect our side lengths, A, B, and C. So notice we've got a connection for our angles, A and B, and we also have our connection with our side lengths, that Pythagorean theorem. And then we're going to be just using trig functions or inverse trig functions to find the rest of the stuff. If you really get stuck with an angle, you can use an inverse trig function. If you really get stuck with a side length, you can use a trig function to set up an equation and solve for that stuff. So trig functions will find side lengths. Inverse trig functions will find angles. Cool? Cool. So here's our right triangle, and here's just some strategies. If you know one of these angles, let's say this one we know. So I'll put a little check mark there. That means we automatically know the other angle because this one is just going to be 90 degrees minus this one, or pi over 2 minus that if it's in radians, because they're complementary. So if you know an angle, suddenly this becomes pretty easy because you can find the other angle very quickly, and then you can find all the side lengths using just trig functions, right? So that'll work out pretty nicely. If you don't know an angle, then hopefully you've got some side lengths, and you can set up an inverse trig function to get that angle. And then if you want, you could set up another inverse trig function to get the other one. But once you know an angle, you can find the other one really easily. And then again, find the remaining side lengths by using trig functions, Pythagorean theorem, all that kind of stuff, depending on what you know. So those are our two kind of main strategies, and I'll show you what I mean by that. So here we know an angle. So right off the bat, I know what this angle is. I know angle B is 90 degrees minus 47.5 degrees. So what's that, 42.5? So let me go ahead and write that in there. So having one angle really is the same thing as having all of them. And I guess I should say really we had two to start because we knew this one was a 90-degree angle. Once we get out of the realm of right triangles, this becomes a little harder, and we'll mess with that later. Notice we also have a side length here. And so if we want to, we can set up a Pythagorean theorem to find the other ones, but the problem is that we have two unknown side lengths there. So the Pythagorean theorem really works nicely if we only have one more to find. So what we'll do is we'll set up a ratio with side lengths, get a trig function. So I'm going to do some sort of a trig function, and I want this side to be in the mix. So, for instance, I'm not going to do tangent of 47.5 degrees because that's going to be, or sorry, tangent would work. I'm tripping, sorry. I'm not going to do sine of 47.5 degrees because that would be our opposite side A over our adjacent, or our hypotenuse, sorry, C. What I want to do is get some trig function that involves 3. So sine is the wrong one if I'm using 47.5 as my angle. What I could do, though, is say, if I look at sine of 42.5 degrees, that should be my opposite side, 3 over c. And that'll help me solve for c. Because I can say, well, that means c is going to be 3 over sine of 42.5 degrees. This is not an angle I just know the value of off the top of my head. It's not one of our nice, pi over 6, pi over 4, pi over 3 angles, or 30 degrees, 45 degrees, 60 degrees angles, or any of the combinations of those all the way around the unit circle. But hopefully you got a calculator nearby. If you don't, go ahead and grab one. By my count, I just whipped this up on my calculator here on my computer. Sine of 42.5 is approximately 0.6756. I'll round it off to 4 decimals. It's really like 5590208, blah, 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 blah. So what I might do is say, all right, what is 3 divided by that? What you could do is just do this all in one shot. Say 3 divided by, sorry, I mixed something up on my calculator, but you can't see that anyways. 3 divided by sine of 42.5. If you do that all in one shot, then we'll get that c is approximately 4.44. That's probably good enough. Now, at this point, you could go ahead and use the Pythagorean theorem to solve for a. You could say a squared plus 3 squared equals 4.44 squared. I wouldn't do that, though. The reason that I wouldn't do that is because this 4.44 is a rounded value. In this class, I really hate rounding things. Here we have to, because we don't have a known angle that we can just get an exact value of the sine for it. But I'm going to try and get my other side length without using that rounded value, which means maybe what I'll do is I'll say something like, let's take a look at tangent of 47.5 degrees in this case. Tangent of 47.5 degrees is going to be the opposite side, A, over the adjacent side, 3. So A is going to be 3 times tangent of 47.5 degrees. So hopefully you can figure out what that is. Again, use your calculator. I pulled mine up already on my computer. So I've got 3 times tangent of 47.5 degrees. That is going to be approximately 3.27, we'll say. Oof, that's pretty bad. Maybe just a quick summarize. I'll write a little summary of my answers over in the corner. So I found angle B. I can just write this. I found that angle B was 42.5 degrees. I'll add the degree symbol in a second. I found that A was approximately... I don't think there's a nice approximate sign. I guess I'll use the tilde here. Screw it. I'll just write it out by hand. So I found that B, capital B, angle B, was exactly equal to 42.5 degrees. I found that side length A was approximately equal to 3.27, and I found that side length C was approximately equal to 4.44. The nice thing is that you can find these values in different ways. If you'd like, instead of using tangent of 47.5 degrees, you could say, let's do cotangent of 42.5 degrees. That'll be the same thing. Or what you could do is say tangent of 42.5, that's going to be 3 over A. So there's all these different things that you can set up. And as long as you've got a calculator where you can actually figure out what those trig function values are, everything should be pretty gravy. So give this one a shot. Notice, maybe I'll set this up first. Notice we don't have an angle. So maybe I'll help you with one angle first. I'll say A is going to be, we know these two side lengths, so I'll use tangent. That's going to be tangent inverse of 9 over 4. That'll work. All right. I'll let you play with that. Find an approximate value for A. Then you can find an approximate value for B. And then you can get an exact value for C pretty nicely. Go for that. All right. And hopefully you paused the video and you're back now. So this tangent inverse, I got to find where my tan inverse is on this little calculator. I don't know if I've got one on here. I'll have to pull something else up. All right, give me 1 sec. All right, I'm back. The calculator that I was using was really, really small. Didn't have even inverse trig functions on there, or at least ones that I could find easily. So if you wanted to, you could say this is approximately, if you want to use degrees, we'll say 66.04 degrees, hopefully you're getting. So then right away we can figure out what B is. B is going to be approximately 90 degrees minus 66.04 degrees, which is 23.96 degrees. So there's our two angles. Hopefully you found C really nicely. C, you can use the Pythagorean theorem for. So again, I wouldn't use these rounded angles to set up some trig equations to get C. What I would do is say that 4 squared plus 9 squared equals C squared. So that means 16 plus 81 equals C squared. C squared then is 97. So C is like plus or minus the square root of 97, but we know it's a positive length, so we'll say C is exactly the square root of 97. So we have some approximate values for these angles. Oops. We've got 23.96 is approximately our B angle. A is approximately 66.04 degrees, but C we know is exactly the square root of 97. Cool. Hopefully that's helpful. So where do we go from here? This doesn't seem too bad, to be honest. Once we have a right triangle, we have some information, we can go ahead and figure out what's going on. So how do things get difficult? What ends up changing? The main thing with these application problems is that sometimes it's hard to get a picture of what's going on. And so sometimes it's hard to exactly see where the right triangle is, or what side lengths are labeled as what, or something like that. Sometimes I'll include some pictures of things. If there's a really tricky situation to kind of get an idea of what's going on, maybe I'll give you a picture of what's happening and you can see the right triangle in there. But sometimes we'll just have to imagine the situation in our head, which can be hard. Sometimes our problems might involve multiple triangles. Maybe they share a side length between them. And so we have to figure out some side lengths of one triangle to get the side lengths of the other. I don't know. Or maybe the angles add up to something that we know. And so we have to figure out one of the angles so we can get the other one. And then the last bit is sometimes it's hard to actually interpret what we're trying to find. Our question might ask for a certain length or a certain angle, but sometimes it's difficult to think of which one we're actually looking for. So maybe we can find all of them, but knowing which one is the one that's required of us can be kind of tricky sometimes. So let me show you a little bit about what I mean here. No picture attached. We're just going to have to visualize this thing. An observer is watching two hot air balloons flying. The balloons are both at an elevation of 1,000 feet. The angle of elevation from the observer to the first balloon is 33.5 degrees, and the angle of elevation from the observer to the second balloon is 14.7 degrees. What's the horizontal distance between the two balloons? What the heck? How do we even start with something like this? This is a hard, maybe a little bit confusing problem. So what we want to do is just start with the two balloons. We know that we've got two hot air balloons flying, so I'm going to draw them. There's one balloon. There's another. They both are at an angle of, at an elevation of 1,000 feet. So I'm going to draw a nice straight line down to the ground. Here's my ground. And what I know is that these distances are the same. They are 1,000 feet. Then I've got some observer. I've got somebody watching right here. I'll say that they're just this little person on the ground. And I know that we've got an angle of elevation to the first balloon. That angle of elevation, I'll draw blue for my sight line. is right here. So I know that this angle is, what did I say, 33.5 degrees. I'll draw my little degree symbol in here. And then I'm going to draw my second angle of elevation in red. This one goes out to the second balloon. And this angle is 14.7 degrees. And what we want to know is what is this distance in between them. Or we can say this distance right here. Same thing. All right, so we have a picture. Does that help us? It should, but there's some tricky stuff going on. The first thing that we might want to notice is that distance that we're looking for, if we look at it on the ground specifically, that's going to be the difference between the base of our red triangle. I'll draw this over here. Here's the base of our red triangle. It's going to be that thing minus the base of our blue triangle. See that? So this distance that we're looking for is our red distance here all the way across. So you can say it's like the horizontal distance from the person to the second balloon minus the horizontal distance from the person to the first balloon. So what we really want to do is find these bottom side lengths. Once we find those, we're good to go. And that's good news because we have the opposite side length of both of these angles. So what we have is in blue, we have that tangent of theta is 1,000 over, maybe I'll call this one, I don't know, x. I don't want to do that. I want to call it a. It's 1,000 over a. And I should change that from tangent theta, shouldn't I? That's tangent of 33.5 degrees specifically. Oh boy, let me just rewrite the whole thing. I'm sorry about that. Oops, I want my eraser. So we'll say tangent 33.5 degrees is 1,000 over a. So a is 1,000 over tangent 33.5 degrees. I'm going to leave that for now. We'll figure out what that is in a bit. Similarly, if we look at this B in red, this one here, I can set up the same kind of thing, and I'll say tangent of 14.7 degrees is going to be the opposite side of this red triangle. That's this one right here, this vertical one of 1,000 again, over B. So B is going to be 1,000 divided by tangent of 14.7 degrees. So my distance that I'm caring about here on the bottom, I'll call this one like X, the thing that I want. I'm going to say this is B minus A. It's 1,000 over tangent of 14.7 degrees minus 1,000 over tangent of 33.5 degrees. We're going to get an approximate for this, but we can go ahead and just type that into a calculator. 1,000 divided by tangent of 14.7 degrees minus 1,000 divided by tangent of 33.5. I keep typing something in wrong, sorry. 33.5 degrees. That should be, let me get rid of something real quick. That should be approximately 2,301. So, the horizontal distance between the two balloons is approximately 2,301 feet. And that's our answer. So we were looking for this horizontal distance between the two. We set up our diagram and we found out that it was a difference between these two bases. We could find the two bases using the tangent function and go from there. That's a lot. It's tough to get a picture. It's tough to visualize what's happening. But once we start down that trail, it ends up getting easier the further we go. Lastly, real quick, how do you use bearings? Bearings are a nice way of just getting some I shouldn't say nice. It's a way of getting some angles. So in a lot of these application problems, they'll be talking about maybe like a plane flying or a ship sailing, and they'll say it's sailing at something like north 35 degrees east. And what that means is that they're going in this direction. If you draw a little north, east, southwest thing, then maybe I'll just label this real quick. There's north, east, south, west. Then what this means is that their angle is this one right here, where this angle, oops, I don't want that, right here, that is 35 degrees. So they're going north, but then they're going 35 degrees east. So if we had a bearing that was south 20 degrees west, then we'd be looking at something like this. Mostly south, a little west, where that angle right here is 20 degrees. Maybe the problem with these is that angle might not be the one that we care about. Maybe we care about this angle. Well, that's easy enough to find. That's just going to be 90 degrees minus 20 degrees. So it's 70 degrees. So we can figure out other angles from these bearings. I don't do a lot of problems with bearings, but you might notice them come up. So I just wanted to show that off really quickly. If you want some more explanation on that, our textbook has a nice little run through of how bearings work. But when you see something like north 35 degrees east, this is what they're talking about. Hopefully that's helpful. Just real quick, if you haven't seen those before, I suspect that some of you have. But if you haven't, that's how that works. Anyways, this problem, I think, is like a big one. I didn't do more examples. If you've got more that you want to see, jump into the text. They've got a couple that are really nice. I like this one because there's no picture, so we kind of have to build it from scratch. The homework problems in the text, the ones that we're going to practice, they kind of build up slowly. So they start with just some nice pictures and no application stuff, and then they jump into some more application problems with some pictures, and then they'll have some like this, where there's no picture, and you just got to read it and understand. So work through those. I would highly encourage you to do those. I think they're very helpful to get an understanding of how that stuff goes. Let me know if you have any questions.